Reverse Osmosis Desalination via Nanoporous Graphene by Caitlin Musick, Harrison Lawson, Brian Jordal, and Andrew Fogel. The need for potable water has become a substantial issue around the world. Out of all the water on Earth, only 3% is fresh water, most of which is in the form of glaciers and snow. Old and current methods of desalination are not capable of meeting the high demand for potable water in an economically efficient way. One of the first types of desalination was thermal desalination. This process uses heat to evaporate water from a saltwater solution while leaving impurities behind. The steam is then condensed to form pure water. Due to water's high specific heat, large amounts of energy are required. This process also has a low production rate because considerable amounts of energy are lost to the environment. Reverse osmosis was then implemented as a form of desalination. In the process, pressure higher than osmotic pressure is applied to a saltwater solution, causing water to pass through a semi-permeable membrane. Salt and other impurities are left on one side of the membrane while pure water collects on the opposite side. By using this process for desalination, efficiency is increased in terms of energy, cost, and amount of potable water output. The first form of reverse osmosis desalination used a polymer membrane, like cellulose acetate or polyamide. These membranes have low salt rejection and low water permeability. These membranes also tend to foul in a short amount of time. The solution to the downfalls of polymer membranes is nanoporous graphene. It has high salt rejection and high water permeability. It can also withstand large applied pressures. Because of these qualities, nanoporous graphene has the ability to serve as a viable reverse osmosis membrane. Graphene is a diverse material with unique characteristics that has caught the attention of scientists and engineers. It is a two-dimensional, carbon-based nanomaterial with layers of carbon arranged in a honeycomb lattice. Graphene has nano-sized pores that can be tailored to a specific size to increase salt and mineral rejection. Due to graphene's structure, it can withstand pressures much greater than what is required for reverse osmosis to occur. Based on this information, it is evident that nanoporous graphene is an ideal membrane for the reverse osmosis desalination process, and some industrial plants have already started implementing it.
The typical reverse osmosis system. There are 4 general steps for the reverse osmosis desalination: intake, pretreatment, reverse osmosis, and post-treatment. Intake is the process in which salt water is fed into the system from a water source. The entire operation from this point on is based heavily upon the quality of this raw feed. When water is drawn from some sources, it can contain concentrations of oxygen that may make it unusable. So an extra step is needed to aerate the water before treatment. In general, the best quality seawater for desalination is drawn from 10 to 15 meters below the surface. The pretreatment process is the next step in the desalination. In the pretreatment phase, acid and chlorine are added to regulate the pH, remove unwanted solids, and prevent bacterial growth on membranes. A flocculator then gently mixes the intake and removes any suspended colloids in the solution via clumping. Sodium bisulfate is finally added to neutralize the solution before the reverse osmosis process begins. After pretreatment, the treated water is sent to a high-pressure pump, where it is pressurized to overcome the osmotic pressure in the reverse osmosis process. The high-pressure feed then enters the reverse osmosis center for filtration. From the first reverse osmosis center, the filtrate is sent to a low-pressure pump and then another reverse osmosis center. The brine from the first reverse osmosis center is sent to an energy recovery device and is later discharged. The filtrate that leaves the second reverse osmosis center then enters a storage tank, and the lower quality discharge is recycled back to the neutralization process to be reused. After the reverse osmosis process, the filtered water's pH is then adjusted, minerals are re-added, and the water is disinfected for drinking. Overall, polymer reverse osmosis membranes are efficient, however, graphene membranes are more efficient. The polymers require extremely high pressures, which makes them inefficient because it costs extremely large amount of money to pressurize the water to the pressure needed to push the water through the membrane, and it's also prone to fouling. Whereas the graphene allows for a lower pressure to be used, and we can actually use less chemicals to treat the water, and we can leave out chemicals that we don't need for the membrane cleaning because there's less cleaning that we need to do with the graphene. Also, the graphene allows for higher production rates because they allow a larger flow of water, and by adding substituents to the graphene, we can substantially make the flow rate even larger.
There are two types of pores in nanoporous graphene membrane, one of which is the hydroxylated pore. Hydroxylated pores have alternating hydroxyl and hydrogen groups, which are hydrophilic in nature. The different pores give different results when it comes to permeability and salt rejection, so it is up to the user to choose which membrane to use based on their own specifications. For hydroxylated pores, the permeability is much higher than that of hydrogenated pores. This is a result of the alcohol groups on the pores that easily hydrogen bond to the water passing through it. On the other hand, hydroxylated pores are less effective at salt rejection. The hydroxyl groups have ion dipole interaction with the salt in the feed water. This raises the free energy barrier, thus decreasing the salt rejection of the system. The other type of pore that are used in membranes are hydrogenated pores. These pores have a lower permeability than the hydroxylated pores. This is a result of the hydrogenated pores being hydrophobic, which causes the entropic effect. This makes the water molecules passing through the pores more ordered and reduces the amount of configurations of the water that the water molecules can form. Because of this, permeability is greatly reduced. In contrast, hydrogenated pores are much more effective at removing salt ions. The hydrogen groups hydrogen bond to the salt ions in the feed stream, which lowers the free energy barrier, increasing the amount of salt that can be rejected. Nanoporous graphene membrane is around 1,000 times thinner than the membranes used in typical desalination systems. This requires the membrane to be very durable, so it can withstand stress put on it through the system. Salt rejection occurs on the atomic level, so the smallest failure in the membrane can result in a whole system failure. There are many different macroscopic properties that affect the durability of the membrane, such as the graphene's elastic effect, Poisson ratios, and fracture stress. The area that receives the most stress is the area around the pores. But graphene behaves in an elastic manner. This greatly reduces the stress at other parts of the membrane. There is also a stress relationship with the pore size, where the larger the pore, the less stress. But if the pores are too large, then there is little to no salt rejection. If the pores are too small, the water molecules will not be able to flow through the membrane, which greatly increases the stress, thus breaking the membrane. This means that an equilibrium point needs to be reached so that there is effective salt rejection and not enough stress to break the membrane.
As explained, thermal desalination is a very inefficient, energy-costly way to desalinate water. This is mainly because of the high specific heat of water, meaning that it takes a lot of energy to bring the water to a boil and vaporize it. More efficient, sustainable methods had to be found in order to supply clean drinking water for a much lower cost. Nanoporous graphene reverse osmosis is that alternative. Because the water is no longer heated in order to desalinate it, the energy is instead used to create high pressure differences across the membrane in order to force the water through it. The salt molecules are much larger than the water molecules, so they are stopped by the membrane while the water is capable of passing through. Before nanoporous graphene, polymer membranes were used to filter the impurities out of the water with reverse osmosis. These polymer membranes often restricted the flow of water through them due to their non-ideal shapes, lowering the amount of water that is desalinated in a given period of time. Nanoporous graphene membranes, on the other hand, are up to 1,000 times thinner than polymer membranes, allowing much more water through while still having effective salt rejection. The structure of the graphene membranes also make them much stronger than polymer membranes and gives them a decreased chance of fouling. They are less likely to become clogged by the impurities or break entirely, meaning that less will need to be replaced, lowering cost. Graphene membranes allow for a much reduced overall cost while also increased potable water output. There are also different types of graphene membranes, mainly hydrogenated and hydroxylated pores. Hydrogenated pores give a much higher salt rejection than hydroxylated pores, but they do not have as high of a permeability, meaning less water moves through them. Hydroxylated pores are the opposite, because they allow for higher permeate flux through the membrane, but have a lower salt rejection. Overall, graphene membranes are a much more plausible, better option than thermal methods or polymer membrane reverse osmosis for the desalination of water. Graphene membranes allow for a much higher flux of water, higher salt rejection, and are more durable than the other membranes.